Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 6, Lesson 1. It's always exciting when we have a Lesson 1 because we're beginning something new. And this new unit is about light and how light behaves, how it travels. And sometimes when light is traveling, it will experience an obstacle. And we're going to talk about what happens when the light travels through something, and then that something, the air, that it's traveling through changes to this. My glass is made of plastic. And then they travel a little bit through the plastic. And then what happens? Then they travel through the air. So that is the main big thing that we're going to be talking about today. So let's do a little bit of vocabulary. Light travels through something, and the thing through which light travels is called the medium. And one fun thing about new vocabulary is, does it sound like another word, or actually is it a word that we've used in other places? For example, I hear the word medium, and I think, oh, my friends who are art teachers use the word medium, right? And I wonder if they just use it differently from the way we use it. So some artists use watercolors, and some artists use clay, and some artists use papier-mâché. And each of those is a medium. They are media, plural. Is that a similar or a different use of this word? Well, I would say that an artist is trying to communicate something, and the material through which they're trying to communicate that, an idea or a feeling in their head that they want to get into someone else's head, the material through which they're doing that communication is the medium. And I would say that as light travels from here to here, it travels through something. So there's this throughness in both art and in science. Well, maybe you're more of a history social sciences person than an arts person. And so, in your history social science classes, you might be learning about the media, which again is the plural of medium. There's print journalism, there's TV, broadcast journalism. These days, the internet has a whole lot of journalism. Each of those is a medium, the internet or a magazine or a newspaper or the television or the radio. Those are all media. Each is a medium through which information is supposed to travel. So a medium in science and history, social science, and in art is always a thing through which something travels. And so I feel like we have a better understanding of the word medium now that we've thought about how the word medium is used in other fields. There's a couple other ways that medium could also be related to the way we use it here in science. See if any of those pop into your head in the next couple or few days. Now, this traveling of light, it is light that is traveling through the medium. That traveling is called propagation. Propagation, to go from one place to another. And you might be, using your history social science brain right now and saying, oh, like propaganda. And I know there's all kinds of connotations of propaganda, whether it's right or wrong or nefarious. But to propagate just means to spread. The propagation of information, the propagation of love, the propagation or the transfer from one location to another of light. So those are a couple really important vocabulary words, medium and propagation. When light travels from here to there, the traveling is called propagation, and the thing through which it travels is the medium. For most of the light in our lives, it's traveling through air. For most of the light's existence, it started being light in the sun, and it traveled from the sun to Earth through what was essentially a vacuum until it got to Earth's atmosphere, and then it traveled through the air. And then it got to my glasses, and then it got to more air. So my question for you, having developed this set of vocabulary, is what happens to light when one medium ends and another medium begins? So I'm going to call this medium 1 and this medium 2. So maybe this was the air and this is the plastic that is my glasses. Or maybe this is the glass that is the window in my classroom. Or maybe it's the glass that's the window of a car. Or maybe it's just, the asphalt on the ground that the light hits. What happens to light when it reaches the end of one medium, some kind of matter that it's traveling through, and gets to a different kind of matter, something else that it might travel through? What happens to light? And I'm going to say the answer is that there are 3 things that can happen to light when it reaches the end of one medium and the beginning of another medium. Now, this line represents what I'm going to call the boundary. There's not 3 places. There's not medium 1 and then the boundary and then medium 2. The boundary separates the 2 media that are in contact. So air and hand are 2 media. Air and plastic are 2 media. The boundary is just where they are in contact. It's not a 3rd place. And I'm going to say there's 3 things that can happen. And the thing that we've been talking about happening is the light just keeps on traveling. It travels from medium 1 into medium 2. It could just continue traveling, and that is called transmission. The light can be transmitted from medium 1 to medium 2, transmission. Another thing that could happen, and I don't know if you can see it very well in my glasses, but sometimes there's a reflection. Have you ever been looking at somebody else who was wearing glasses and you could see yourself reflected in those glasses? The light from you came to the glasses. Some of the light traveled through so I could see, but some of the light bounced off so you could see yourself. And so this reflection, transmission, could happen. Reflection could happen. That's terrible handwriting. reflection. And a third thing that could happen, instead of the light continuing to travel or changing direction and staying in medium 1, the light could stop traveling. Light is just moving energy. And instead of moving into medium 2 or staying in medium 1, it could just stop traveling and it could just stay at this location and be absorbed as energy, in which case this location would warm up. So I'm going to call that absorption. So the 3 things that can happen to light when it's traveling in a medium and that medium ends and another medium begins. It can continue moving into the second medium, we call that transmission. It could stay in the first medium, we call that reflection, or it could stop moving altogether and turn into a different form of energy. Light is moving energy, so if it stops moving, it's not light anymore, and it'll turn into another form of energy. If it hits a solar cell, it might turn into stored electrical energy. If it's just hitting something like the asphalt on the ground, it's just going to turn into heat energy. If it's absorbed by something green, like the leaf of a plant, you can ask your biology teacher what kind of energy that is stored as. All right, so the 3 things that can happen. Now, light is energy. So if I have 100 joules of energy, all 100 of those joules are going to do one of these 3 things. And depending on what this medium is and what this medium is, and also depending on the angle that we hit the boundary at, but depending on those things, that's going to determine what % is transmitted, what % is reflected, and what % is absorbed. But I promise you, these 3% will always add up to 100%. All the energy does one of these three things. All right. I think that's enough on that topic. I'm just going to check on how I'm doing on time. I'm doing okay on time. Next topic is called the law of reflection. So when the light stays in medium 1, it does not enter medium 2, it just bounces off of it. I'm going to talk to you about the law of reflection, the way in which we reflect. And what I showed there at first was kind of boring. The light went in, and then it comes back along the same path along which it entered. I'm going to autofocus. That looks better. But sometimes the light comes in at an angle like this. I have this arrow indicating the direction the ray of light is traveling. This is my ray of light. This is my boundary. And can you, now we're not going to be transmitted, we're just going to be reflected. Can you predict the path that the ray is going to take? I bet you have an idea. I bet you think it's going to travel like this. And you're right. And the law of reflection is what tells me what's going to happen here. So what I'm going to do is I'm going to draw this segment. This segment is called the normal. And there's many normals. Normal means perpendicular. Normal means perpendicular. And there's many, 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 many normals, but there's only one normal that crosses the boundary where the ray hits or where the ray is incident. This is the point where the ray is incident. I-N-C-I-D-E-N-T, like a thing that happens, an incident. Or it's the location of incidence. Lots of vocabulary today. So this normal contains the point of incidence. And what we'll see is that this angle here and this angle here are congruent. This angle is called theta sub I. We call that the angle of incidence. This angle is called theta sub R, and it's called the angle of reflection. And theta sub I is equal to theta sub R. Or maybe I should say they're congruent. Angles are congruent. This is the law of reflection. Isn't that exciting? Pretty obvious, right? Now, a couple things that are going to be useful. These two angles, the angle between the ray and the normal, the angle between the normal and the ray, are congruent. Are these two angles, this one here X and this one here Y, are they also congruent? Yes, they are. But we are not going to talk about these angles, the angle between the ray and the boundary, the angle between the boundary and the ray. For right now, it really doesn't matter, but I promise you later on in this chapter, if you talk about this angle instead of this angle, you'll get all the answers wrong because we're going to do some trigonometry. So I'm just telling you, get used to these angles, the angle with the boundary. And that will help you get all the answers right later on in the chapter. So that's the law of reflection. Now, one drawing that we could make that's really pretty is if I have a boundary and if I have rays of light that are parallel to each other. I tried to draw that so these rays are parallel to each other. And when they reflect, they all follow the law of reflection. And they're still parallel. The incoming rays are parallel. The outgoing rays are parallel. Very pretty. That is called specular reflection. One thing that's fun about lesson 1, the first lesson in a unit, is that we get a lot of new vocabulary. And that looks really pretty. Now, what doesn't look as pretty, maybe, I guess pretty is in the eye of the beholder. What if my boundary is kind of bumpy? Sometimes in older houses, the windows are not so smooth anymore and they get bumpy like this. And if I have rays of light that are parallel, that come in and hit this surface. They come in, the incoming rays, the incident rays are parallel. Will the reflected rays be parallel? They're not going to be parallel. It's going to look really messy. So what I have to do is I have to draw a normal. Oh, this one's just going to reflect right back. And I'm going to draw, oh, look at the normal here. Well, this one's going to follow the law of reflection. Do you see how I followed the law of reflection? I made these two angles equal to each other. This one, oh, this one's going to get reflected pretty much straight back again. And then this one, when I follow the law of reflection. So my incoming rays were nice and organized and parallel, and my outgoing rays are not parallel. That's called diffuse reflection. We've got specular reflection, and we've got diffuse reflection. Specular reflection, the best example of that is a mirror. Mirrors are super smooth, and they give us this nice, organized reflection. Now, sometimes a surface might look smooth, like my very young-looking skin, right? You're like, oh my gosh, Dr. Platt, you only look 16. I'm a little older than 16, even though my skin looks very, very smooth. But if you were to look at it under a microscope, please don't, it would end up being really bumpy. So what that means is that the light can come in and hit me. And even though the light is all organized and coming in nice and parallel, it's just going to go off in every direction. It's just the light that bounces off is going to be a mess. And you're like, well, why is that useful? It's actually useful so that the light will bounce off of me in all these different directions, and everybody in the room, regardless of where they're seated, gets to see me because I'm reflecting light in every direction. So this diffuse reflection turns out to be really useful. And specular reflection is useful, in the bathroom when you're, brushing your teeth. But it doesn't reflect the light everywhere. So two different kinds of reflection. As you're noticing light bounce around in your house, you might see one versus the other. I have these little tables in my living room that I can set a beverage on. And they're just really pretty. They have a mirror on the top surface, which is hard to keep clean, but I do because they're pretty. And sometimes the light shines in and it hits this table, and I can see a little square of light on the wall. But when light shines in and hits the couch, it doesn't make a couch-sized reflection on the wall. The couch will just reflect the light in all directions, but a mirror will reflect the light in a very specific direction. So look around you in your world and see if you can see examples of specular and diffuse reflection. But it's important to notice that for both kinds of reflection, we follow the law of reflection. The law of reflection is a law, and we follow it in all the situations. All right, so the final thing we're going to talk about now is pretty mind-blowing. I know you've heard about the speed of light. And the speed of light is a universal constant. The speed with which light travels is actually 1, 2, 3, 1, 2, 3. It's 300,000 meters per second. 1, 2, 3, 4, 5, 6, 7, 8, or 3 times 10 to the 8th meters per second. That's the speed at which light travels. It's really fast. That is the speed of light in a vacuum. It turns out that light travels this speed in a vacuum, and in other media, it travels a little bit slower. In some media, it travels quite a bit slower. So this universal constant, the speed of light, It's very important. But that is the speed of light in a vacuum. Light travels slower than this in air. It travels slower than that in water. It travels slower than that in glass. Oh my goodness. And so maybe you've heard this, or maybe you haven't, but it's really important to know that light travels at different speeds in different media. Just like me, Dr. Platt travels at different speeds in different media. When I'm running, I travel at one speed, through the air on the asphalt. When I'm swimming through the water, I'm a terrible swimmer. When I'm swimming in the water, I travel more slowly. So light is like that. It travels at different speeds in different media. Your car travels at different speeds in different media. It travels at 25 miles an hour, faster, in residential neighborhoods. It travels at 55 miles an hour, faster, on the freeway. Okay. So different speeds for different media. Now, the way we express that is with an equation. We take the speed, now this speed of light, 300,000 meters per second, 3 times 10 to the 8th meters per second. The speed in a vacuum, we call this letter C. I don't know why C, because speed and light don't have any C's in them. But the letter lowercase c is reserved for the speed of light. So we take that speed and we divide it by the speed the light is traveling in this slower medium. And we call that ratio lowercase n. All of these are lowercase letters, small c, small v, small n. This number c is a constant. It is always 3 times 10 to the 8th. This number v is the speed in whatever medium we're talking about. And this number n is just a comparison of those speeds. Which is faster, c or v? C is faster, right? I said light travels slower in other media. So if c is faster, what kind of number do you think this fraction is going to be if the numerator is bigger than the denominator? It's going to be a number bigger than 1. N is bigger than 1. If it's just a tiny bit bigger than 1, that means this is just a tiny bit slower. If n is a lot bigger than 1, it means we're in a medium where the light travels pretty slowly. So a big value of n means light travels slowly in that medium. A small value of n means light travels closer to c, closer to this maximum value, the speed of light in a vacuum, in that medium. And the smallest value that n can be is exactly 1. And if n is exactly 1, that means v is exactly c, and we're traveling in a vacuum. So here are some examples. N equals 1, vacuum. I'm going to write this. N equals c over v. This is worth memorizing. So n, oh, by the way, I may have been using this vocabulary already. N is called the index of refraction. Don't worry about that word refraction. I'm going to teach you that in the next lesson. The n is called the index of refraction. It is a number. No unit. It is dimensionless because the unit for speed, c, is meters per second. The unit for speed, v, is meters per second. And meters per second over meters per second, everything canceled. That's dimensionless. No unit, dimensionless. All right, so for a vacuum, n equals 1. For air, n equals 1.00, something small, like 1.002. For water, N equals about 1.3. And for glass, different kinds of glass are different, but in general, around 1.5. So you can see N increases where the light travels slower, and N decreases and approaches 1 as the medium gets closer to being a vacuum. So right now, all I want you to know is that light travels different speeds in different media. And the way we talk about how much slower it travels than the maximum speed, 3 times 10 to the 8th, is by looking at this ratio of the two speeds. And we put the fast speed on top, so we're expecting N to be numbers bigger than 1. Okay, that is all I have for you today. I hope you've enjoyed this discussion of light traveling in different media. Have a wonderful day, and whatever you do, don't break the laws of physics.